Hello, folks. I'm Mr. Pinola. Are you a swimmer or do you know someone who is a swimmer? Well, maybe they've gotten frustrated because they can't swim in their pool because their pool is too short. Well, if you take a look on your screen, you'll notice a device that might help them with this kind of a situation. Now, this is not an advertisement in any way. You'll see where this ties into the physics. But this is a device called the endless pool. And basically, it's a device that I'm circling with my mouse here that basically sends out a stream of water that works against a swimmer. And this way, the swimmer can swim forward and feel like they're traveling great distances, but not actually go anywhere. So theoretically, you could swim for a long time in this setup and really not travel anywhere, but still use a ton of energy to get there. Let's take a look at what a setup of this would look like. This is a very simplified diagram, and obviously this is a very dangerous diagram that we have here. The endless pool is a much safer device the way it's designed. But essentially, there is a large turbine or a fan that's creating some kind of current that the swimmer will attempt to swim through. And so in the endless pool, there would certainly be a box around this because we wouldn't want the swimmer hitting the blades of the turbine. But the swimmer would swim forward, they would swim at a certain speed, whatever speed they're capable of, and there would be a current moving at a certain speed against them. And as a result, if the speed of the current working against the swimmer and the speed of the swimmer were exactly the same, then the swimmer would be able to swim for a very long time without really moving anywhere. Sort of like if you were on a treadmill. The treadmill moves at a certain speed and you walk at a certain speed. And doing that, you get your exercise and still stay in the same spot. So let's take a look on the board today about how this works and about how this relates to the concepts of speed and velocity that we've been talking about. We've already covered in this class that speed is a measurement of how fast something moves. But up until now, we've always talked about another word that we've said is basically the same thing as speed. It starts with a V. Do you know what it is? It's velocity. And velocity is the reason that we use V, for example, to represent speed in our three-step equations. But velocity is slightly different from speed. And today we're going to discuss that difference. Now, velocity is also a measurement of how fast something moves. But notice I didn't put a period at the end of this sentence. The definition for speed ends here. The definition for velocity does not. Velocity is, in fact, a measurement of how fast something moves and which direction the object is moving in. So, speed and velocity, basically the same thing, except velocity gives you more information because velocity, in addition to talking about how fast something moves, also talks about the direction that something is moving in. Maybe there are some words from earlier in our unit which come to mind. Do you remember the words vectors and scalars? Well, that's sort of like what we have going on here. Speed is very specifically a scalar measurement. And that's because when you measure something's speed, you measure how fast it is moving. That's the magnitude, the amount of the speed. But you don't measure direction with speed. We don't talk about direction when we refer to speed. And so that's what makes speed a scalar measurement. It includes magnitude, but not direction. Velocity is different, however. Velocity is not a scalar measurement. Velocity is a vector measurement. Do you remember what two things make up a vector measurement? If you said magnitude and direction, you'd be correct. And that's because when we measure your velocity, we measure how fast something moves. That's the magnitude, the amount of your velocity. And we also measure which direction you're moving in. So since velocity includes direction, in addition to the magnitude or the amount of the measurement, velocity is considered a vector measurement, whereas speed is just considered a scalar measurement. An easy way to remember this: speed starts with an S, as does scalar measurement. Velocity starts with V, as does vector measurement. Now, let's reconsider our example that we showed at the top of the video, where we had the man who was swimming in the endless pool, that pool that was sort of like a treadmill for swimmers. Well, we know the man was staying in the exact same spot, so he wasn't moving. Essentially, if you don't move, doesn't that mean your speed is basically zero? But how can that be? The man was swimming at a certain speed, and there's also speed coming from the water of the endless pool. Well, what's going on here is that we have to look at combining vectors via vector addition, which is something that we talked about a couple classes ago. Do you remember that a vector is a measurement that can be represented by an arrow? Well, that's true about velocity as well. So let's see if we can take a look at how vector measurement or vector addition works for the man swimming in the endless pool. I'm going to use a meter stick to make sure that our arrows are straight. And I'm going to show a man that is swimming to the right at a speed of 3 meters per second. Now, when you draw your vectors using a ruler, it's a good idea to make sure your vectors are to scale. To make my measurement of 3 meters per second, I used a scale that every 5 inches on my meter stick here would represent 1 meter per second. That way I can judge the relative sizes of the vectors. Now, that's the speed that the man can swim at. But the endless pool is working against him. And the endless pool is sending off current at a speed of exactly 3 meters per second. We know that because the man's not moving. And so as a result, the endless pool sends a current in the opposite direction at exactly 3 meters per second. You'll notice that I connected the vectors head to tail. So basically, I started the second vector, or the tail of the second vector, at the head of the first vector. Remember, when you're doing vector addition, always add vectors head to tail. And so, if the man swims out at 3 meters per second and then back at 3 meters per second, do you remember from earlier when we talked about displacement that we have to pick one direction when the vectors are moving the opposite way to be negative? Well, let's pick the direction backwards to be negative. So in this case, we would add the vectors 3 meters per second going to the right, which would be a positive measurement, plus negative 3 meters per second going to the left, which would be a negative measurement. As a result, 3 plus negative 3 gives us an answer of 0 meters per second. And so we would say that in this example, the velocity of the man is 0 meters per second, because we found the velocity by using vector addition. That's why the man doesn't move anywhere. His velocity is 0 meters per second. And normally with velocity, you would put a direction measurement with this, but since it's 0 meters per second, we're not going to include left or right because he's essentially not moving. Now let's consider a slightly different example, again though with our man swimming in the endless pool. This time, we're going to imagine that the man is very strong and he's swimming very fast. So let's say that our man can swim with a speed of 4 meters per second. So now he's using his body more. Maybe he's kicking his feet and moving his arms a little bit more, and he can swim, if this was a normal pool, at 4 meters per second. Well, the endless pool is still turned on, and so the endless pool is still going to be working against the man. So I'm going to add the endless pool vector head to tail. But the endless pool is still on at only 3 meters per second. Notice now that the man is moving faster than the current working against him. If I do my vector addition, I would have 4 meters per second plus -3 meters per second. And I would add them up and find that 4 plus -3 is +1 meters per second. And notice that positive means that I'm going to the right in my diagram, because I made the 3 negative. So that would mean a velocity of +1 meters per second is essentially a velocity of 1 meters per second to the right. So if the man were to swim faster than the endless pool working against him, he would move forward. Now, he wouldn't move as fast forward as if there was nothing working against him, because otherwise he would be going at 4 meters per second. But since his speed is faster than the endless pool working against him, he is going to still move at 1 meter per second to the right, as we can find from our vector addition. Let's consider now one last example. This man, let's say, swims forward, and let's say he's swimming at his original speed. So we said in the first example that the man's typical swimming speed is 3 meters per second. But now somebody has cranked up the energy on the endless pool. And now the stream of water going against him is going at a whopping 5 meters per second in the opposite direction, obviously, from where the man is. So once again, I'll scale my measurement. And I will draw the 5 meters per second vector from the endless pool head to tail with the original vector I drew in. What will happen now? Well, if the current is too strong, the man is going to be moving backwards. It might look like he is still trying to swim forwards, but since the current is so strong, he might be moving his arms this way, but he's going to move backwards, and eventually his feet will kick the back of the pool behind him, and he'll move in this direction because the current was too strong. And so if we add our vectors once again, we would have 3 meters per second in the positive direction, but then 5 meters per second in the negative direction. As a result, 3 plus -5 is like the same thing as 3 minus 5, and I would get -2 meters per second. Notice in my diagram, negative meant to the left, and so this means that his velocity, v, is essentially 2 meters per second to the left. Just as we talked about before, velocity has a magnitude, in this case 2 meters per second, and a direction to the left. Now remember that first example I showed you where the man was swimming at 3 meters per second and the current was going exactly against him at 3 meters per second? Well, this is something that fascinated the Mythbusters, which was a TV show that you may have seen. They aimed to test out different scientific theories, and they thought about this kind of example, where you would have one velocity vector going one direction, as I'm showing you here with the mouse, and another velocity vector going the other way. And so that's exactly what the Mythbusters tried to do. They set up a situation where they took a truck and they put a cannon in the back of the truck that would shoot a soccer ball outwards in the opposite direction. And they set the truck to a certain speed, in this case, 60 miles an hour. And they had the truck going towards one side, and they had the cannon being fired towards the other side. And so they said, if we add up our vectors, the soccer ball being shot out of the cannon would be 60 miles per hour to the right, and the truck would be moving 60 miles per hour to the left. 60 plus negative 60 would equal 0. It would basically be like the cannon, or the soccer ball that was shot out of the cannon, basically wouldn't move. So it should just stop the second it leaves the cannon and just fall straight down. Well, that seems a little strange. So here's what the situation looked like. They set up a checkerboard background, and they would have their truck move really fast in one direction. And the ball was fired from the cannon at 60 miles per hour in the opposite direction. Watch this GIF to see what happens. This is obviously in slow motion, but the second the cannonball gets fired, it basically stops and falls straight to the ground. Let's watch it one more time. The vectors were going in opposite directions, and so the resulting, or the net velocity of the soccer ball came out to be 0 because the vectors for the velocity were going in opposite directions. Let's take a look now at one last example. This example is going to be one that shows you how to do velocity vector addition in 2 dimensions, where something is moving kind of up and down and left to right at the same time. We're going to imagine that we're looking down on a river, and the river is moving towards the right. And so that means that there is a current in the river. If you were to observe a piece of, or a leaf, let's say, in the river, the leaf would move towards the right along with the river current. We're going to say that the river current in our example is 4 meters per second to the right. Let's say that you start out here on the shore, and you want to cross to the other side, and you take your boat and you aim your boat straight upwards, trying to get to the other side of the river. And let's say that your boat can travel at a speed of 3 meters per second. Will you get to the other side? Well, you will, but there'll be a bit of a problem. You're going to end up a little bit further on down the river than you originally wanted. That's because the vectors are going to combine now in two dimensions. Let's take a look at what that would look like. So we're going to draw in our vectors. And let's say that here is your speed, 3 meters per second. I should say your velocity, 3 meters per second north. And then we have the speed of the river current. Which is 4 meters per second to the east. Notice I added my vectors head to tail. I stuck the tail of the river velocity vector to the head of your velocity vector. Well, we're going to draw in the resultant, or what your actual speed would be. And I'll do that using orange. To show the resultant, we go right from the start to the finish. And notice what we have. Your boat would travel at an angle because of the combination of velocity vectors. How do we find the amount of speed that you would travel at? Well, this is a triangle. In fact, it's a right triangle. And it is a 3, 4, 5 right triangle. Why? 3 squared plus 4 squared equals the unknown value squared. This is the Pythagorean theorem. And so the unknown mystery velocity would be 5 meters per second to the northeast. And that's because we would figure out the value of the missing vector when we have to consider 2 dimensions by making a triangle and using Pythagorean theorem, which you might recognize as a squared plus b squared equals c squared, to figure out this missing value. Thanks for watching, folks. I hope you learned something today about velocity and speed. Remember, speed is a scalar quantity because it does not include direction, whereas velocity is a vector quantity because it does include direction.